Hi, this is Brandon Baines, the Math Department at Lipscomb University, here to talk with you today about linear programming. In this presentation, you'll learn how to find optimized values of a given quantity using linear programming. When we talk about optimized values, we're talking about either highest values, we would call that like a maximum value, or lowest values possible. So that would be what some people call a minimum value. Linear programming is a method for solving these types of min-max optimization problems. And in particular, it's when our variable of interest is constrained by other factors. In applied scenarios, you may think of if it takes, say, 30 minutes to bake a loaf of bread, then you are constrained by time in terms of how many loaves of bread you can bake per day. There's only so much time, so you're constrained there. Other types of constraints could be things related to amounts of ingredients. If we stay with the bread kind of thought, if I only have 2 bags of flour, then I'm constrained by the amount of flour that I currently have. When we're looking at these optimization problems, the function that models the variable to be optimized is often called the objective function. It's the function that models our variable of interest. The constraints in the problem form a system of linear inequalities. And the big idea with the linear programming is that the optimized value for our objective function must come from the solution to the system of inequalities. The graphical solution to the system of inequalities is called the feasible region. So in a linear programming problem, the solution must come from the feasible region. Let's consider an example scenario and see how this all comes together. A certain aircraft can carry no more than 60,000 pounds. The aircraft is used to transport bottled water and medical kits for disaster relief. The bottled water weighs 20 pounds per container, and the medical kits weigh 8 pounds per kit. Each plane can carry no more than 6,000 containers and kits altogether. Each container of water serves 10 people, and each kit serves 6 people. We want to determine the number of containers of water and the number of medical kits the plane should carry in order to maximize the number of people helped. Our objective function in this scenario, we'll call it P. I'm just using P to represent people helped, would be given by 10x plus 6y. That's because the scenario tells us that we have 10 people helped from each container of water, and so we're using x for the number of containers of water, and 6 people helped from each medical kit, so y we're using as the medical kit here. The constraints in this problem are that we can only take 0 or more containers of water. We could take none, but none or something positive. We also have the same constraint on the number of medical kits. We could take 0 medical kits, or we have to take some. We also have the constraint given by the inequality 20x plus 8y must be less than or equal to 60,000. I'm going to toggle back to see where that inequality comes from. And this is related to weight, because our aircraft can carry no more than 60,000 pounds. And the weight of the water is 20 pounds per container. And the weight of the medical kits is 8 pounds per kit. The last constraint in this problem is x plus y is less than or equal to 6,000. And that comes from the scenario when it says that each plane can carry no more than 6,000 containers and kits all together. All right, so the value that will optimize the number of people served must come from the solution to this system of inequalities. And furthermore, when in linear programming, it must come from one of the vertices of the feasible region. So one part of our problem here will be determining where those vertices are. So below we have the graph. I used Wolfram Alpha to graph all of our inequalities. And so we see the feasible region here in front of us. Any of the ordered pairs in the region or on the border of the region will satisfy all of the constraints. But in a linear programming problem, the vertices are the ordered pairs of interest. Each of these vertices, I'm using vertices just like we would in geometry. Each of those vertices are potentially the values of x and y that will maximize the number of people served, and potentially the x and y that will minimize the number of people served. In part 2 of this presentation, we'll look at how we're going to find those vertices.